Okay, we're finally talking about using the electrode, ion selective electrode to be precise, to measure voltage and determine concentration of nitrogen in solution. So the technique for measurement involves measuring exactly 50 milliliters of solution whose voltage you want to determine. It can be a standard solution or it can be an unknown. And then we must add 1 milliliter of what's called ionic strength adjusting solution, or ISA. Do not confuse ISA with ISC. I know it's somewhat similar, it can be confusing, so I'd like to reiterate that ISC stands for ion selective electrode. So ISC here is what we're using, the device we're using to measure. ISA stands for ionic strength adjusting solution. It's a solution that we have to add to our tested solution prior to conducting the measurement of voltage, because in solution there are many ions, and all these ions are present in various concentrations. And if those ions are not present in sort of one uniform concentration, the voltage may get affected. So what we're trying to do is we're trying to create sort of a baseline of concentrations of all the other ions by introducing ionic strength adjusting solution. So anytime voltage is measured, ISA must be added. For this experiment, if you read the procedure, you will see that we're using 2 molar solution of ammonium sulfate, which of course is NH4,2SO4, as our ionic strength adjusting solution. So what I will want you to do in your report for this is I want you to calculate how many grams of ammonium sulfate will be needed to make exactly 100 milliliters of 2 molar solution. I'm not going to make it, I have some here, so I'm going to show you how I'm using it. But you would have to find how many grams of ammonium sulfate is needed in simple calculation. You have molarity, you have volume, so you can find number of moles and then just convert to grams. Don't forget, the formula of ammonium sulfate is NH4,2SO4. So now we're going to move over here where I can show you the setup I have over here. Over here, please, so we can see the setup and the display. So let's take a look at our experimental setup. What I have here is the ion selective electrode. It is right here. The electrode has a solution inside with certain precise concentration of nitrate ion. The membrane is right here on its bottom. Let me turn it around so you can see. Just take it off. So right here is the membrane. It's this brownish gray disc on the bottom of the electrode. And so when I place this electrode in a solution with certain concentration of nitrate, the voltage will be read on the display of the data logger. So electrode is hooked up to what's called a chemistry sensor, and this is our passcode data logger. And I have it set up to where it's measuring my voltage in millivolts like we discussed. So I'm going to show you how the measurement could be done. So right now what I have here is the special soaking solution that I store my electrode in. And I'm going to get out my store bar with my magic fishing stick. So in this graduated cylinder, I have pre-measured, as you can see, exactly 50 milliliters of my unknown solution. I could use a standard if I wanted to. I'm just choosing to show you an unknown measurement. So I'm going to place this in a clean, dry beaker. As I mentioned earlier, we must also add ionic strength adjusting solution. So I have another pipette here with another bulb. This is my ionic strength adjusting solution. Students usually make way more than they end up using, so I had my previous sections pour the remaining ionic strength adjusting in this container, and as you can see, it says 2 molar ammonium sulfate. Hopefully you can see that, and in parentheses it says ISA, ionic strength adjuster. So I'm going to pour some of this solution into the small beaker here. And remember, I need 1 milliliter of this. So once again, we press A, depress the bulb, and then I press S and suck my solution in until it's above 0. Then I'm adjusting the volume so meniscus is right at 0. And then I'm going to hold the pipette over my container with the sample that I poured in. I need 1 milliliter, so I'm going to press the empty valve, and I'm going to get it to where it's right at 1. So I've added 1 milliliter of my ISA. So I'm going to set my beaker with the sample on the stirring plate. This is a magnetic stir bar. I'm going to carefully add it, and then I'm going to turn on my stirrer. As you can see, the bar is moving, stirring my solution. Continuous stirring is typically required to obtain as accurate of a measurement as we possibly can. The way this works is there's a plate made of iron underneath the surface of the stir plate, and when I turn this on, the plate starts rotating, and then the bar is magnetic, so it picks up the magnetic field and rotates with the plate underneath it. So now I'm going to simply lower the electrode into my solution. You will notice that the way I have it set up, the electrode is immersed in solution, but is not being hit by the stir bar. So this is how you would set it up as well if you were doing these measurements. And as soon as I placed my electrode in the solution and started measuring, you can see the voltage has changed. It was roughly 167, I think, before, and now it's down to 225 now, 0.7. This is jumping around a little, so typically you have to wait about, I don't know, 3 to 5 minutes before recording the voltage. So again, you would, in actual lab, prepare 4 standards, measure voltage of each, and then you would measure voltages of all your unknowns, including any water samples that you would have brought to lab. Unfortunately, we don't get to do all this. So now I'm going to go ahead and show you the type of data you can expect to see, and we're going to discuss the graph, how the graph would look like. So originally, when I conducted this experiment a while ago, I actually prepared 5 standard solutions. No, 6. So I had one standard whose concentration was 20 parts per million nitrogen, 10, 5, 2, 1, and I also had 0.5. You're not going to have this one, and you're not going to have this one. So we're only looking at these 4 standards here. Our range of concentrations for standards goes from 1 to 10 ppm. And then notice what I did in my Excel table. I didn't just have my ppm and my voltages of ion selective electrode. In between, I created an extra column where I calculated log of concentration of ppm. This is log with a base of 10. It's not natural log. It's very important. So what you have to do is find logs of these concentrations. I will post this file on Canvas for you, so you can take a look and see what kind of data I have. And your data, at least for this column and this column, will be very similar. You will probably get a different set of voltages here. So looking at these data, what can we say? If you recall, we discussed the relationship between voltage expressed in millivolts and concentration of nitrogen expressed in parts per million or milligrams per liter. And I mentioned that because of how Nernst equation is set up, we would expect that increase in concentration of nitrate, increase in concentration here from bottom to the top, would cause decrease of voltage. And that's exactly what we're seeing here. As you can see, the standard with the lowest concentration of 0.5 ppm nitrogen had the highest voltage. And as concentration of nitrate increased from bottom to the top, the voltage happens to be decreasing. So the solution with the highest voltage is the solution with lowest concentration, and the solution with lowest voltage is the solution with highest concentration. So how would that look like in terms of our graph? So if you graph your data, this is what it should look like. So let's first talk about what you would have on your axis. On your x-axis, you should not have concentration of nitrogen. Instead, you should have log of concentration. So again, it's very important because the linear relationship is not between concentration and voltage. Instead, it's between log of concentration and voltage. And here we have voltage of an ion selective electrode in millivolts. And then when we graph our data, what we get is linear relationship. So again, you would need to create a scatter plot with a linear trend line. You will notice here that this trend line has a negative slope, which is what we expected, considering increase in concentration causes decrease in voltage. And I'd like to point out also this here is Nernst equation, the one that I had on the board earlier, and you can see that voltage is equal to standard voltage or constant minus K times log of concentration of nitrate. So as concentration of nitrate increases, voltage decreases. And this is the equation I got from this particular set of data. According to manufacturer's specifications for this electrode I showed you earlier, the slope of this graph is expected to be negative 55 millivolts or close to it. And usually I calibrate the electrode before students use it to make sure that the slope is somewhere close, probably plus minus 5 millivolts near negative 55. My particular electrode at the time when I was collecting these data, I got negative 54.1, which obviously is very close to negative 55. So I know my electrode was working properly, giving me expected slope. So once again, to reiterate, I'm going to send you data showing voltages for 4 standards. You're going to calculate log of concentration for each standard, and then you're going to create a graph like this, plotting log of concentration of nitrogen in parts per million versus your voltage, ISC voltage in millivolts. I should say ISC voltage versus log of ppm. So once you have the graph, you can then get the equation of the line The equation should be somewhat similar to what I have here. The y-intercept here might be very different for yours, but slope should be somewhere close to negative 54. Last thing I'd like to discuss, let me just quickly bring the screen back up. I wanted to discuss the calculation. So for my solution over here, my voltage now is 227.6. Let's say we use my equation that I just had on the board. It was negative 54.1 roughly, x plus 267, I think, something like that. So how do we use this equation and value of voltage for our unknown? How do we use these to find concentration of nitrogen? So clearly we would have to plug in voltage into y here, so 227.6 equals minus 54.1x plus 266. I'm sorry, 267. It's getting late. What I'd like to point out that I hope you can rearrange this equation and find x. So here from this equation you find x. What I'd like to point out though is x is actually log of concentration of nitrogen. It is not concentration yet, right? Because in our Nernst equation we had log, and our graph had log on the x-axis. So how do we find concentration of nitrogen from here then? The answer is we would have to take 10 to the x. So you have to remember to do this in your report. If I give you the voltage for the unknown, you will plug it into your equation of the line, solve for x, and then don't forget to do an extra step where you find concentration of nitrogen in ppm by taking 10 to the x. I hope I was clear enough in my explanations. I am planning on holding virtual office hours via WebEx, hopefully sometime next week. So when you start working on this, and if you have any questions, you can of course talk to TAs by email, and hopefully we'll be able to connect on WebEx Live. I will announce this on Canvas. Thank you very much, everyone. Have a great week.